Hi, in this video we're going to be looking at right-angled triangles and how their sides and their angles are related to each other. Okay, this is the study of trigonometry, how the sides and angles of a triangle relate to each other. There's a fantastic little mnemonic which I hope you're familiar with, which helps you to remember the relationships between the sides and the angles, internal angles of a right-angled triangle. It's SOHCAHTOA. SOHCAHTOA breaks up into three sections, and each of the sections describes one of the three possible relationships between the sides and the angles. The first one is SOH, which stands for the sine of an angle theta, and one of the internal angles. This little symbol here means, we call it theta, it's a Greek letter. The sine of theta equals OH, the opposite side divided by the hypotenuse side. I'll spell out hypotenuse and opposite this time, but in the future I'm going to be abbreviating those. So opposite and hypotenuse, opposite divided by hypotenuse. So that's the first relationship, sine theta. What it says is that when you take the sine ratio, which is a special function on your calculator, the sine ratio of one of the internal angles, like this one here, sine theta 1, if you take sine theta 1, it will equal the opposite side, this side over here, opposite to the angle, divided by the hypotenuse side, which is this one here. So in the case of our example triangle, that's going to be sine theta 1, this angle, equals side B, the opposite side, divided by side C, the hypotenuse. Okay, we'll come back to this later, but we'll just stop there and say that's the first relationship in SOHCAHTOA, in trigonometry. Okay, the second part of SOHCAHTOA is CAH, and this stands for cos theta, the cosine of an internal angle, equals the adjacent side divided by the hypotenuse side. So again, let's look at our example triangle over here. We've got an angle, and for cosine theta, this is a different relationship to sine theta. We are going to look at the adjacent side, which is the side right next to the angle. This is side A. Although C is also adjacent, we never call C the adjacent side because it's the hypotenuse. It's always the hypotenuse because it's the longest side. So this is the adjacent side here, the one next to it. So in our example, it's going to be cosine of theta 1, we're talking about that angle again, is going to be the adjacent side, which is A, divided by the hypotenuse, which is C. So that's the second relationship. Lastly, we've got TOA in SOHCAHTOA. TOA stands for tan theta, the tangent of the theta, equals the opposite side divided by the adjacent side. So if we are talking about this angle here again, tan theta 1, the adjacent will be A and the opposite will be B. A divided by B. So those are the three relationships that are really fundamental to trigonometry. If you can remember that, then you're most of the way to understanding trigonometry. Most of the problems that you'll see in trigonometry are a simple matter of writing out SOHCAHTOA and then figuring out which of these three relationships you need to use in order to work out the problem, and then substituting in some values into one of the equation that you've chosen. So let's do an example of that now. Okay, let's say we've got a right angled triangle, and this angle here is 30 degrees. We know that. We know the hypotenuse, the long side, is 9 meters, but we don't know either of these sides. Let's try and use one of these equations to find side x to begin with. Okay, we're trying to find side x. Now if we look at the angle that we've got, the x is opposite to that angle. So we know we're going to need the equation, one of the equations that's got opposite in it. There's two, there's tan and sine, both have opposite in them. So we've got to decide which one. We've also got the hypotenuse that's been given to us. So we know that the equation should have the opposite and the hypotenuse, and that of course is that's got sine theta equals opposite divided by hypotenuse. So since we've got the since our equation involves the angle, the opposite and the hypotenuse, that's the one we should use. So we'll substitute in the values we've got. Sine 30 degrees, put those values in. The opposite we don't know, it's x, and the hypotenuse is 9 meters. So that's the equation we come up with. Now we can try and solve for x. So we cancel out the 9 that's around the x, put 9 times on both sides, and we get 9 sine 30 degrees equals x. Okay, all we've got to do now is put this into a calculator and it will give us the value of x, the side length. Okay, here we are with our Casio ClassPad calculator. Now before we do this calculation, we just want to check that we've got the calculator set onto degrees down here. We don't want it set on radians or gradients or anything else. We want to make sure that we've set it on decimals, so it's going to give us a decimal answer down here, and we're going to need the keyboard to enter this in, so I'll bring up the keyboard there. Alright, now 9 times sine of 30, and it knows that's 30 degrees because I've told it down here that I'm doing degrees, and then enter, and it tells me the answer is 4.5. So 4.5 meters equals x. Alright, now why don't you pause the video, grab a pen and paper, and see if you can find y using one of these equations. I'll give you a hint, it's not going to be sine because we've already used sine. That was for finding the opposite. For finding y, it's going to be a different equation. So pause the video now, have a go at that. Okay, how did you go? So you were trying to find y. That would mean that you're trying to find the adjacent side to the angle. So the equation should have adjacent in it. There's two equations that have adjacent in it, cos and tan. Both have the cos and the tan equations have that in it. And since the other thing that we know is the hypotenuse, then probably the best one to use is the cos equation. It's got the adjacent and the hypotenuse. In fact, now we also have the opposite side, so you could have used tan, which includes the opposite and the adjacent, because you now have the opposite side. But let's say we didn't have that, we'd have to use cos. So we'd end up with cos theta equals adjacent over hypotenuse. We'd put in our values. Cos of 30 degrees equals the adjacent side, which is what we're trying to find out, y, divided by the hypotenuse, which is 9. Then we've got to solve for y, so we multiply both sides by 9, and we end up with 9 cos 30 degrees equals y, and we need to put that into a calculator. So we'd have 9 times cos 30, close bracket, and enter, and it comes out to 7.794 meters equals y. So there we go, we've got all three sides of that triangle now. And obviously if we'd had an equation where we knew either the opposite or the adjacent but not the other one, and we knew the angle, we would have used tan. Now let me also show you how you can use the SOHCAHTOA equations to find not just the sides but also an angle. Let's say this other angle here that we don't know, let's call it theta. Let's say we wanted to find that. We can use one of these equations to do that. And in fact, now that we've got all three sides, we can use any of the equations we want. Let's try the tan equation this time. Okay, tan theta equals the opposite side divided by the adjacent side. Okay, let's put in the values that we've got. We don't have theta this time, so that remains unknown, it remains theta. but we do have the opposite side to theta, which is 7.79 meters, and we also have the adjacent side, which is 4.5 meters. Remember, the adjacent side is always the short side, it can never be the hypotenuse. So 7.79 divided by 4.5. Okay, now we need to put that into the calculator, so 7.79 divided by 4.5 equals 1.73. That equals tan theta. Now what we're after here is the theta itself. So we need to get rid of this tan thing here so that we've got theta on its own. And the way to do that is to use this function here, inverse tan. It's called tan to the power of -1. It's the opposite of the tan function, so it will, if we apply it to both sides of this equation, get rid of this tan here that's around the theta and tell us what theta is. So since we've got tan to the -1 on this side, we've got to apply that to the 1.73. Let's do that. So I've told it to do tan to the -1 of the answer from the previous question. That's what that little answer button's there for. Execute that, and it gives us 59.98 degrees. Now, if we're clever, we might realize that it's very, very close to 60, and we would know that the reason that's close to 60 but not quite is 60 is because when we use these values back here, we had to round them off a little bit. So they weren't perfectly accurate, and we also rounded the 1.73 value off as well. If we'd done it, if we'd used exact values all the way along, then we would have had exactly 60 degrees. But let's just go with what the calculator's told us. Theta equals 59.99 degrees. So we've just found the unknown angle. Now if we come back to our triangle, we can see that answer of 59.99 degrees, or let's say it's 60 degrees, that makes sense because we know that angles in the triangle have to add up to 180, and we've got 90 here, 30 here, that's 120, so this one had to be 60. We could have already guessed that using our previous knowledge, but we've just confirmed it using SOHCAHTOA. Okay, the next thing we need to remember or revise is Pythagoras' theorem, and hopefully you remember this off by heart. It's really easy. A squared plus b squared equals c squared for any right-angled triangle. So what that tells us is if we've got a right-angled triangle with sides a, b, c, c is always, we always label c the long side, the hypotenuse. If we've got a right-angled triangle, then the square of side a plus the square of side b will equal the square of side c. So let's do an example. If we've got a right angled triangle and this side is 3 and this side is 4, then our equation a squared plus b squared equals c squared. We substitute in the values. 3 squared plus 4 squared equals c squared. 3 squared is 9, 4 squared is 16, so that equals 25. So 25 equals c squared. To get c on its own and find the value of c, we've got to take the square root of both sides. The square root cancels out the square. So we've got to take the square root of both sides. The square root of 25, if you put it into a calculator, is 5. So c equals 5. And obviously we could use Pythagoras' theorem to find any of the three sides. As long as we have 2, we can find the other one. Now it turns out that there are certain angles which, when we put them into sine, cos and theta, sine, cos and tan, certain angles will give us exact value answers. So those angles are 30 degrees, 45 degrees and 60 degrees. Whenever we take the sine, cos or the tan of any one of those angles, we'll get an exact value as the result. Now, what I mean by exact values is things exactly unlike this number here. This is not an exact value, it's a really long decimal that just keeps going on and on and on. You'll often see those when you do things in your calculator. But an exact value would be something like this, the square root of 2. Okay, when you put it into your calculator, actually the calculator will render it as a really long decimal. But as mathematicians, as human beings, we can visualize this thing as being exactly what it is, exactly what it says, the square root of 2. So we're not approximating it, we're saying it's exactly that. That's what I mean by an exact value. 1 is also an exact value. Okay, and here are those exact values of the trigonometric identities. So the sine of 30 degrees will give you half. The sine of 45 degrees will give you the square root of 2 over 2. The sine of 60 degrees will give you the square root of 3 over 2, and so on. And you can see how they would apply to cos and tan as well, and the results that you would get. Now, don't panic, because there's no need for you to memorize those identities. If you need to use them, then they'll be available to you. Okay, the last new thing that I'll introduce to you are these 3 bits of, I guess you'd call them trigonometry trivia. Okay, the first one is the Pythagorean Identity. It simply says that the square of sine theta plus the square of cos theta equals 1. It always equals 1. It doesn't matter what the theta is. As long as you square the sine and the cos individually and add them together, you'll get 1. This is actually a restatement of Pythagoras' theorem, but just explaining it in terms of sine and cos. And if it seems a little bit weird to put the squared there after the cos instead of after the angle, that's just the way it's written. It means the whole thing, the whole cos theta has been squared and the whole sine theta has been squared. The second one shows how sine and cos are complementary functions, which, if you think about it, it can kind of be understood, because anytime you change one side of a right angled triangle, anytime you change the angle by making one side bigger or smaller, you're going to change the other side. Okay, and for any given triangle, if that's the opposite and that's the adjacent side, then we know that sine relates more to the opposite side, cos relates to the adjacent side. So as soon as you change the sine for the opposite side, you're going to change the cos, which relates to the adjacent side. So the functions always give and take from each other, and these are 2 equations show how that's true. The third bit of extra information is the tangent function, expressing it in terms of sine and cos. Okay, these three things together are explained in a lot more detail later in this video, but if you're happy just to accept these 3 equations as they are, then there's no need to watch that 10 minutes. You might even find it confusing, but it does. I do explain later on how each of these 3 equations come about and what their significance is. You can watch that if you like, or if you want, you can skip over it. So let's summarize everything that we've seen so far in this video. Okay, to finish off, here is a summary of the trigonometry of right-angled triangles that we've looked at. So we've got the 3 laws, or the 3 equations that come from SOHCAHTOA that show us how the angle of a right-angled triangle relates to the 3 sides, SOHCAHTOA. We've got the exact values for certain angles that are produced when you put 30, 45 and 60 into those 3 sine, cos and tan functions. And we've got these 3 kind of special identities, or special features of trigonometry: the Pythagorean identity, the sine and cos are complementary functions expressed in these equations, and that the tangent function can be expressed as sine theta divided by cos theta. As I said, these 3 extra bits that we've tacked on at the end, if you want more of an explanation of those, the last 10 minutes of this video will explain it, but if you're not interested in seeing that, it's not necessary to watch it. It's entirely optional, and at this stage you won't be expected to use these functions. All that's required at the moment is that you recognize them and that you know what they are. You won't have to include them in any problems in this section. So don't stress about them just yet. Okay, thanks for watching the video. I hope you found it helpful. Okay, the last thing I'm going to introduce in this video, this introduction to trigonometry video, is just a couple of other random bits and pieces. So the first one is what's called the Pythagorean Identity. The Pythagorean Identity states that the square of sine theta plus the square of cos theta will always equal 1. Okay, now this might look a bit strange because the squared is not on the end, but it's the whole thing that's being squared. It's just the way it's written when you're squaring a sine function or a cos function or a tan function for that matter. The squared goes next to the sine, but it's the whole thing that's being squared. Now that can be easily proven, and I'll write it down, but you don't have to know this, so if you're not interested in it, you can feel free to skip over it, but here it is anyway. The way we can prove that this is true is by remembering that sine theta equals the opposite over the hypotenuse, and that cos theta equals the adjacent over the hypotenuse. Okay, and if we substitute those two identities, those two relationships into this equation, here's what we get. Instead of sine squared theta, we'll have instead of sine squared theta, we'll have OH squared. And instead of cos squared theta, we'll have AH squared. Okay, because sine theta equals OH, I've just replaced the sine theta with OH, but it's got to be squared. Same with cos theta. And that all equals 1. I've got my squared there. Okay, now if we expand this out, then we get OH times OH, that's O divided by H squared, plus A divided by H times A divided by H. And that gives us O squared over H squared plus A squared over H squared. Just multiplying the top by the top and the bottom by the bottom in both cases. Now this can also be written in another way. We can make that O squared plus A squared divided by H squared. Just putting the two H's together on the bottom here. You're allowed to do that. Okay, and then we find that what we've got up here, if we remember that this is all coming from a right angled triangle, we've got the opposite angle. If that's theta, then we've got the opposite side rather, the opposite side squared plus the adjacent side squared. And if you remember your Pythagoras theorem, the opposite side squared plus the adjacent side squared, the two short sides squared and added together, will equal the hypotenuse squared. So this is actually equal to H squared. So we could rewrite that equation as H squared over H squared. This is Pythagoras' theorem on top here that's allowed us to do that. H squared over H squared, hypotenuse squared over hypotenuse squared, which equals 1. Anything divided by itself will always equal 1. So that's how we end up getting this result. When we started with those two things and added them together, we got 1. And we showed that that was true by going through this process. We ended up with 1. Okay, like I said though, this is the thing that you need to know, the Pythagorean identity. That bit you should have some understanding of. The explanation of how it was obtained, it's not necessary for you to know that. That was just for your interest. But this identity, sine squared theta plus cos squared theta equals 1. You need to remember that. You might have to use it at some point in the future. Okay, the next random bit of trig trivia that you need to be aware of is complementary functions. And so I've written out here the two equations that demonstrate how sine and cos are complementary functions, how they kind of work in tandem. They work side by side. There's always a link between sine and cos, and that link, you can kind of see it in this table by the fact that for sine of 30 degrees we know that that sine of 30 degrees is going to be a half, and if we look over here at cos of 60 degrees we find that that's also a half. We find these pairs in the relationships. We see that cos of 30 degrees is the same as sine of 60 degrees, and when sine and cos are applied to the same angle, then you get the same result. You get the square root of 2 over 2. Okay, so we see that there's these pairs of relationships with sine and cos. Now the best way to make that more clear is to look at an example triangle. So let's make up a right angle triangle. Again, it's poorly drawn, excuse my drawing skills. And let's put an angle of 30 degrees there. Now, if this is the hypotenuse, of course this is the opposite from the angle and this is the adjacent. If we do sine of 30 degrees, then of course we're talking about the opposite over the hypotenuse. So we'd be referring to this side over here. And sine of 30 degrees, according to our table, is going to equal a half. Okay, and we find sine theta here in this complementary function. It says cos of 90 degrees minus theta should give us the same result. So let's test that out. Let's do cos 90 degrees minus 60 degrees. Sorry, minus 30 degrees rather. That was what theta was. And that's going to equal cos 90 minus 30 is 60. So cos of 60 degrees. And if we look at our table, we see that cos of 60 degrees is half. Okay, so the table's saying that they're the same. But does that make sense according to the triangle? So if sine of 30 degrees equaled this opposite side over here, then if we did this other angle up here, which is 60 degrees, and we took cos of 60 degrees, then cos theta equals adjacent over hypotenuse. Cos theta equals adjacent over hypotenuse. So in this case, the adjacent side is this one again. Before it was the opposite because we were looking at this angle, but now with this angle, it's the adjacent. So we find that as long as the hypotenuse is the same here, in this equation and this equation, which it is because we're dealing with the same triangle, then the adjacent here and the opposite here are both going to be this side. That's going to be exactly the same. So that shows you why this equation is true. But really all it means is whenever you've got a sine or a cos, you can find out what the alternative would be just by doing 90 degrees minus the angle that you've been given. Whatever the angle here is, just do 90 minus that angle. And the other function, if you were using cos at first, then you'd use sine the second time, it will yield the exact same result if you do 90 minus the angle. That's all it's saying. Okay, lastly we're going to look at the tangent function and a special relationship that only applies to the tangent function, which is this. Tan theta can also be expressed as sine theta divided by cos theta. Okay, now that's really all you need to know, that that's true. But if you're interested, I'll show you how it's true. If you want, you can skip over this bit, but if you like, you can watch it. So if that's supposed to be true, then we should be able to say sine theta divided by cos theta is the same as opposite over hypotenuse, which is, if you remember your SOHCAHTOA, sine theta equals opposite over hypotenuse. So sine theta equals opposite over hypotenuse divided by cos theta, which is adjacent over hypotenuse. That shouldn't come as a surprise to you, that cos theta is adjacent divided by the hypotenuse. So let's try and expand this out and see where it takes us. Anytime you've got a fraction divided by a fraction, you can rewrite it by flipping the fractions upside down, or rather flipping one of them upside down and multiplying them together. Okay, that's just something you would have learned in earlier years of mathematics. If you've forgotten it, then you can go check it out in your Year 7 maths book. Alright, now once we've got a cross multiplication like that, it's a lot easier to work out. We do top times top, which gives us OH, and we do bottom by bottom, which gives us HA. The H's on the top and the bottom cancel each other out, and we're left with opposite divided by adjacent, which, if you remember your SOHCAHTOA, is what tan theta equals. Opposite divided by adjacent. So we started with tan theta equals sine theta and cos theta, and following that through to its logical conclusion, we ended up with opposite over adjacent, which we have already established earlier is what tan theta is. It's equivalent to tan theta. So that's another bit of tangent trivia. Okay, and here's a bit of a summary of the stuff that we covered in this video, so you can write that down if you like. Probably need to pause the video, and thanks very much for watching. Okay.